So this. Very good. So first of all, probably you have seen on the website we have uploaded project proposals. So you can find, maybe I can actually show it here. So we have uploaded a PDF document where we basically list 3 different project proposals. You can start looking at them. Actually, you do not have the tools now to complete the projects. After today's lesson, we will, when we basically finish TinyOS and TOSSIM, you may actually start to think about doing one of them if you want. And anyway, sorry? Well, even the day before the deadline, if you're, you don't have, well, it's better that you send an email to me announcing which project you would like to do, right? But I mean, you're free to choose whenever you want, basically. So if you go on the website here, on the support material, you have here a PDF file with all the project proposals. Okay, so with general rules and instructions on what you have to deliver and this kind of stuff, and the description of the projects. Now, I will not enter into the details of this now. I will leave this for the last lectures, okay? But you can start, if you want, reading on them and decide whether if you like them or you want to do something else, or you do not want to do the project at all. And I have also uploaded a set of supplementary material for these projects. For example, some of the projects require to build an application on top, for example, of an accelerometer sensor. Since you do not own any of this hardware, I have simulated the output of a sensor, and I have put the code, TinyOS code, on the website that you can use in your project. We will see today how to import, let's say, a fake sensor into a wireless sensor network simulation. Okay, so you can download also the supplementary files from here. Anyway, I will be more specific on this topic during the last lecture that we will have at the end of this course. Okay, so I will go into the detail of each of the projects and explaining what you should do, what you should implement, what you should deliver, this kind of stuff, okay? But they are there, so you can start looking at them. Very good. Now, what we have to do today. So, the last time we started looking at TinyOS, okay? So we saw the basics, how to set up a very simple application, how to compile it in order to produce an executable that you can load either on the hardware or on the simulator in order to see what's happening, okay? And if I remember correctly, we saw how to use timers, okay? How to control basic devices such as LEDs, okay? Turn LEDs on or off. And we also saw how to communicate on the radio, okay? So how to transmit and how to receive messages. Now we will start from this basis. We will basically introduce some new elements, in particular how to read from a sensor, okay, which is very easy again. But the main topic of today's lessons is how to use the TinyOS simulator, which is called TOSSIM, okay. So last time we saw that We have the Kuja simulator, which is built for Contiki, but we can use it anyway for TinyOS as well. Today we will use the official, let's say, TinyOS simulator. So we will see how to set up a simulation, how to run the simulation, and how to print debug statements and this kind of stuff. Then we will see how to interface the simulation with a program which is running on a PC. Okay, so this is to simulate the behavior of a sensor network which at a certain point has to deliver the information to a remote location. Okay, and in order to do this, we most likely will pass from a PC or a gateway or something which is connected to the internet. Okay, so I have some slides as well prepared for this lecture. Okay, this one. And of course you can also open the virtual machine, since most of the stuff that I will show is it's based on examples that we have on the virtual machine. Very good. So any question on the past topics in the meantime? No. So I'll stress again why it is important to simulate, okay, application for wireless sensor networks before actually going into the field and test and see whether it works or not. So typically we have very, very large deployments, okay, up to hundreds or thousands maybe of wireless sensors which communicate with each other. And these deployments are usually located in places which are difficultly accessible, okay, like a bridge, a volcano, some forest in some place, okay. So what we would like to do is to deploy the network just once and just when we know that the application that we are going to deploy is working properly, okay. So it does everything we want it to do. There are no bugs. We can, you know, expect that it will work exactly as the way we developed it. Okay. And again, when something bad happens, okay, typically it's really a mess. Okay, because either you have to go there, and first of all you have to see whether if you can spot where the bug is, okay, so where the error is, and then if you are lucky to spot it in any way, you have to deploy again the sensor network, which is very time consuming, and since time basically equals money, we want to minimize both, okay, these aspects, okay. So again, there's very, very little room for redeploying if some error occurs, okay. So again, why simulating? Well, because we want to check the correctness of the application. That's it, okay. And well, it's not like also checking the correctness of an application, even in simulation, is not an easy task, okay. Why? Well, first of all, because you are programming for a sensor node, okay, for a very, very limited hardware in terms of resources. It's not like you are programming for a PC where you have nice development environments, you can set breakpoints in your code, you can debug, you can inspect the content of the variables at runtime, okay? So it's a complete different world, okay? So even when you want to debug an application in simulation, it's very hard to do it. And if you read this TinyOS programming guide, you know, you remember the one that I pointed you probably in the first lesson. Yeah, there's this nice, very, very funny sentence which says, okay, if you want to debug, you have to prepare to a painful experience, okay? It's very hard to understand what's happening on the sensor node, especially because you have very, very little output, okay? So if you think about a sensor node, what's the output that we have? Well, we have the LEDs. We don't have any screen, actually, okay? Unless we decide to simulate and put some prints statements. Okay, that's what we learned today. Sorry. So at the same time, we have several advantages in simulating. Okay, we can study the system in an environment which is controlled by us, meaning that we can set up the radio links, we can set up, for example, the expected transmission, let's say the expected packet loss between sensor nodes. We can observe, or meaning we can inject particular types of packets in the network. We can decide to set some conditions as we want in order to see whether the system reacts properly or not. Okay, so all this is a pro. Okay, simulating allows to basically decide for some, let's say, boundary conditions to check whether your application is running properly or not. Okay, while in the real field, well, you are basically constrained from the actual condition that you have. So you don't have, you cannot actually, unless you are God, you cannot decide what's happening, right? We can observe interaction which are difficult to capture live, exactly because you can set proper conditions. So for example, if you have a bug that happens only when a particular condition appears, you can enforce that condition during simulation, while if you have the system deployed in the reality, you have to wait for that particular condition to happen, and this may be also unlikely. Okay, and of course there are a lot of other pros in simulating. So we can write the application once, test it, then understanding that, okay, maybe it's better if we rewrite this part in this way in order to have a little bit of more efficiency or this kind of stuff. And of course we have also disadvantages. Okay, I mean, comparing a simulation and a real life deployment. And of course the first one is that, well, a simulation of course may not represent the real life. Okay, we are not able to simulate with a 100% accuracy what's happening in real life. Okay, so let's say simulating helps. It will help to prevent the majority of bugs, but I mean, you cannot simulate real life. And of course, especially for the radio part, so where you try to simulate radio transmission, it can differ a lot from the real life depending on the assumption that you made on the actual radio environment. Okay, so for example, you can simulate that you have a certain signal to noise ratio between a transmitter and a receiver, and you can check what happens in that condition. But then when you go into reality, you can have that the signal to noise ratio is really time varying. Okay, you can have that a lot of stuff can happen that you can't simulate actually. So so simulation is, I would say, mandatory. Okay, but still, since it cannot model real life with 100% accuracy, you can have some bugs that always will snake into your code. Okay. Now, when it comes to simulate for wireless sensor networks, I don't know if the telecom guys here have simulated something for PC network at this point. Yes or not? So no one has used NS2, NS3, Omnet simulators for PC, proper PC network, like Ethernet network or wireless network. So, well, if you go out there and see what you can use for simulating networks in general, there are a lot of tools which are, let's say, meant to be used for computer networks, either wired or wireless. Okay. So you have all this kind of tool, NS2, NS3, Omnet, which are basically simulators for computer networks. Okay, you can select many parameters, you can do whatever you want. So if one is, let's say, used to simulate computer networks, the first thing that it may do is, okay, why don't we use these kind of simulators also for wireless sensor networks, okay? And the answer is that, well, they are too much, okay, for what we need, and at the same time they lack some functionalities that we need, okay? So they are not the proper tool. Exactly like using an existing operating system is not okay for wireless sensor network, and we have to develop our own operating systems like TinyOS, Contiki, and this kind of stuff, okay? Just because we are working with a technology which is unique for some way, okay? So, for example, all the simulators are very, at some level, complicated to use. For example, you have to specify what kind of radio chip you are using, what kind of network interface you're using, what is, for example, the attenuation on the cable that you are connecting to computer with, and all this kind of stuff. And also the learning curve, I mean, the time that you spend in order to learn how to use the simulator is really, really a lot, okay? So it's not that good unless you have to simulate PC networks. And also, and this is one thing that I will stress a lot, these simulators have their own programming languages, okay? It means that in order to set up a simulation, you have to basically rewrite your, I don't know, network protocol or network application that you are testing with the language that these simulators accept, okay? So this is bad because, for example, if your hardware supports a certain programming language, you have to rewrite what the application that you have in mind in another programming language, which is the one supported by the simulators, and then you have to test it with that programming language, okay? So you can understand that just by translating from one language to the other, you can mess things up, okay? So you can, you know, just because you are not maybe used to one programming language, you insert some bug, or you remove a bug, so you don't see that bug on the simulation, but then when you come back to your hardware, you will have it, okay? So we really would like to have the same exact implementation both in simulation and in real life. So like what we did last time with Kuja, okay? We just compiled the simulation and then we run it into the simulator, okay? That was the exact same implementation. So that's why they came up with TOSSIM, and after that with other simulators like Kuja, for example, or like the one that Motrunner has. We will see this in a couple of lectures. So we have the TinyOS simulator, TOSSIM, okay? Now TOSSIM is as many other simulators, is a discrete event simulator, meaning that time in the simulation is basically discrete, okay? So the flow of time is not non-continuous like in real life, but it's discrete, okay? The nice feature is that it uses the same code that you use to program the sensors, okay? So we write the code once and then we can compile it for real-life deployment or simulation, okay? But the code is exactly the same. And we can set up the simulation using two different programming languages, either Python or C++. Now, all the examples that I will show are based on Python since it's easier, okay, to set up. Now, the requirements that we have for a wireless sensor network simulator, and I would say that TOSSIM respects, are the following. So, well, probably one of the most important is that we want the simulator to be able to manage a lot of sensor nodes at the same time, okay? So we like to have very, very large deployment to be tested in simulation, up to thousands of nodes, for example. And of course, we want it to be as complete as possible, okay? So we want it to, model the real life that we will observe in the most accurate way, let's say. Okay, we will see that we can actually do a lot of stuff with TOSSIM. It's interesting. Now, probably from now on, I will move to the virtual machine. Okay, so I will try to show you stuff directly into the virtual machine without going, forward and backward within the slides and the simulator. Anyway, just as a starting point, if you remember, we have seen also this with Kuja. The starting point of a simulator is setting up a network. Okay, so deciding how many nodes your network has, what is the type, let's say, of these nodes, and how the radio environment is structured, meaning that what is the network topology in terms of links between nodes. Okay, so which nodes can communicate with which other nodes, basically. And we will start exactly by looking at this. So in TOSSIM, what you do in order to set up the simulation is to write a text file that contains the network topology. Okay, and I will show it to you now. So network topology is something like this. Okay, so you have nodes which can be deployed into space, and two nodes are connected by a link if they can communicate. Okay, and moreover, you can specify what is the I would say strength of this link. Okay, you can have good links, you can have bad links. If you have a good link, all the messages, all the packets that will be sent from the transmitter will be received by the receiver. Okay, if you have a bad link, you have what is called a packet loss probability. Okay, meaning that a certain amount of packet will be lost during transmission, and you can control this value. Okay, so setting up a topology in TOSSIM basically boils down to deciding what are the links between nodes and how good they are. Okay, that's it. So for example, if you have node 1 and node 2 in your simulation, and you want to set a link between those two, you will add a line on this text file saying, okay, I want a link from 1 to 2 with this signal strength. Okay, and we will see what this number means. Basically, the lower this number, the better the link. Okay, so this is a good link, I would say. When you start moving towards -80, -90, it's becoming a bad link. Okay, it's basically, this number is the received signal strength which is observed by the receiver when a packet arrives from the transmitter. Okay, in dBm. Okay, but we will see this in details. So let's go back to the virtual machine, or maybe let's do this first. So what I would like to do is to show you the simulator with an application. Okay, this is the easiest way of understanding what's going on. So imagine that we have a transmitter and a receiver. Okay, so, or basically two nodes. Okay, the first one is asking a request to the second one, asking for some measurement. Okay, and this request packet will be acknowledged by the second node. Everyone knows what is an acknowledgement, right? Okay, right? Who doesn't know what an acknowledgement is? Okay, good. So the first one will send a request that will be acknowledged. Okay, and after the request, the receiver will sense a sensor, so we'll sample some data from the sensor, and in this case we will just generate a random value since we do not have any sensor here, we're just simulating, and we'll put this value in a response packet that will be transmitted to the first node, and again this packet will be acknowledged. Okay, so I want to simulate this application. It's something like a server-client application where the server asks for values from the client, okay? And all these requests and response are acknowledged. So imagine that I want to do it in TinyOS, okay? Since we have seen at least the basic blocks. What components I would need for implementing this application? Anyone? At least the main components. No one? So do I need the component for turning on and off LEDs here? No, right? Well, let's see the code. So you have in this folder here IoT examples, TinyOS, and send ACK. This is the folder for this application. I will open the implementation and the configuration. Okay, so this is the implementation. So the interface that I'm going to use are the boot interface, which, as you should know now, is a mandatory, basically, interface that you use to boot the system up. Okay, I will use interfaces for turning on the radio and modifying the content of the packets that I want to transmit. This is a new interface, the packet acknowledgements interface. You can understand from the name what it does, basically. I will use the AM send interface to transmit an active message. Split control is basically used to turning on the radio. I will use the same code for both the nodes, okay? So both nodes are actually transmitting and receiving, and depending on the type of node or on the message that will be received, I will, differentiate the code. So you have both the transmission and receive interface. Then I have a timer and a new interface, which is the read interface, okay? And it is used to, read data from a sensor. Okay. Now let's just look at how the wiring is. Yes. No. AM stands for active message, which is the basic, let's say, message abstraction in TinyOS. Okay. If you remember last time, we have seen that an active message channel basically is like a TCP port, more or less. And if you use this kind of abstraction, sending messages is very, very easy. You just need to specify on which channel you want to transmit, and if you want to transmit in broadcast or with a particular unicast address. Okay. Now, let me also open the wiring configuration. If you remember, the wiring for TinyOS basically connects the interfaces that you use in your application with components in the system, okay? So the boot interface is always connected to the main C component, which provides the function for setting up the system. Then I have, as you can see, the sender, the active message sender and the active message receiver on this channel, okay, which I have called AM my message and is specified in the header file. It's basically a number, okay. Then I have the split control interface, which is used to turn on or off the radio, connected to the active message C. These are the interfaces for accessing packet fields, okay. Then I have a timer here, because we will see that these requests are will be sent with a timer, okay. So each, I don't know, 100 milliseconds or something like this. And then I have the read interface, which is connected to a new component which I have written, and it's called the fake sensor, okay. So basically this component just produces a random number, okay? So when you read on this component, you will read a random number, okay? So we will look at it maybe later. So let's see very, very quickly what the application does. We have some new guys here also, the tasks, okay? So do you remember, probably in the first lesson I have talked about tasks. Why do we need tasks in TinyOS? Okay, so tasks are basically functions, okay? So it's a piece of code that your application can execute. The very important difference between tasks and actual functions is that tasks are executed in an asynchronous manner, okay? Asynchronous manner, meaning that when you decide to execute a task, and in order to do this you have to post the task will not be executed in that exactly same moment, but it will be put into a queue, okay? And the scheduler of TinyOS will decide when it is the best moment to execute the task, okay? Now, this kind of deferred execution in this asynchronous way is useful because typically you use task for intensive operation, like I don't know, processing on data, or operations that will require a certain amount of time. Now, if you don't do like this, you are basically blocking the CPU in a very intensive operation, meaning that other operation cannot be executed, like a timer that fires or a message that arrives, this kind of stuff, okay? This is because TinyOS have this scheduler, which basically what it does is basically it interrupts everything which is working at that moment when an event arrives, okay? And tasks can be preempted, okay? So can be interrupted, but events cannot be interrupted, okay? So if you try to, so let's think about this situation. You receive, you read the data from the sensor, okay? The sensor will provide an event, so will fire an event when the data is ready. At that point, in the event, you try to process the data. So you are basically executing the code for processing the data into the event, okay? Since you are into the event, another event that comes, for example, another timers that fire, another message that arrives on the radio, cannot preempt what you are doing, okay? It means that you are stuck in the data processing routine, and you cannot do anything else, okay? That's bad, because you can miss important events. Instead, you should take the processing functions and put them into a task, okay? So basically, with this deferred execution, you read from the sensor, you post a task which basically execute the processing, okay? And the scheduler now is basically can interrupt the task when another event arrives. In this way, you are much more flexible in managing events, okay? So you should use tasks a lot, and you should use tasks in order to perform intensive operations, basically. In this case, this is just an example, and we will use the task to send a request message or send a response message, okay? Which are not intensive operation, but it's just an example. So when you basically declare a task, well, it's just a container at this point when you put some code inside. But let's start from the starting point of the application, which is the boot event. So it is an event which is triggered by the operating system when everything is ready. At this point, you start the radio with the split control, because we need the radio here, so it should be started. And when the radio is correctly started, another event will come back from the operating system here, the start done event. So we can see what's happening inside this function. If the radio was started correctly, then, well, let's see before this branch. Now, if the radio wasn't started correctly, then we have to try to start it again, okay, to start it again. Otherwise, let's see later what is this DPG statement. Otherwise, what I will do, I will check the ID or the address of the node in the simulation, basically, okay? Now, this is something very, very it's basically a trick that you can use in TinyOS, and we will see why it's useful. So each node in TinyOS has an ID, okay? It's basically a number, okay, from 0 to whatever. Actually, from 0 to 65,500 something, since it's a 16-bit unsigned integer, okay? So you can give IDs to your nodes in order to differentiate them their behavior in the simulation, okay? So in this case, and coming back to our slide, this is node 1, okay, with ID 1, and this is node 2, for example, okay? So it's node 1 that will send requests to node 2, okay? So, sorry, if I am node 1, and to understand whether I'm node 1 or not, I have to check this system variable, TinyOS node ID, which contains the ID of the node. So if I'm node 1, I will start a timer, okay? In this case, it's 800 milliseconds. And what happens when the timer fires? As you can imagine, I will try to transmit a request, okay? And in fact, when the timer fires, I will post the send request task. So I will tell the scheduler that I want to execute the code inside this function, okay? So let's see what it does. Send request. I will create a message, okay? And the message is of type myMessageT, which is probably specified in the header file here. So the message that I will transmit is a 3 fields message. The first one is a field that tells the message type, which can be basically a request or a response. Then the message ID, which is just an ID of the message. It's basically an increment, a number which is continually incremented. And then there's a value in the third field, okay? So I will set that the message type is a request, okay, since this is node 1, which is transmitting requests. And I will just put as a message ID the variable of a counter, which I continuously increment, okay? Then I will also request an acknowledgement for the packet that I have, that I want to transmit, okay? We will see, this is very useful to use, so it will trigger an event to be fired if the acknowledged is then received, okay? That's very good because we can understand if our packet was received or not from the receiver, okay? So we can then behave properly. For example, retransmitting the packet if we need. And then I will try to transmit, okay, my packet, in this case to node number 2, okay? So if you remember, the send command of the AM send interface accept the address of the destination, and this could be a broadcast or a specified TOSS node ID, basically. In this case it's number 2, and then you have, of course, to specify what packet you have to transmit, okay? And here we have a bunch of stuff that we will see just in a while. Very good. Now let's see what happens when we receive something. Well, sorry, actually, before. When you call the send command, then you have to wait for an event, which is the send done event. Okay, so the send done event will tell you the basically what is how the transmission was performed basically. So we will check in this case if we received an acknowledgement. Okay, so if the packet was correctly acknowledged, we can stop the timer. Otherwise, we can send another request. Okay, so it's basically working like this. If you send a request and for some reason an acknowledgement doesn't come back, you will send another request. Okay, when you receive an acknowledge, then you stop the timer. So basically you will not send requests anymore. Okay, that's it. Now on the receive side, so we have seen let's say till here, till the acknowledgement went back. Now the nice thing is that you don't have to worry for acknowledgements. It's TinyOS that manages that part for you. Okay, you just use the interface acknowledge. You don't have to actually implement the acknowledgement transmission and the acknowledgement reception. Okay, you just use the interface packet acknowledgement, and that's it. Now on the receiver side, so I have the receive interface, which will fire an event each time a message is received on the radio. So what I will do, I basically check the content of the packet, and you will see what this means. And then if the message that I have received is a request message, it means that I am node 2. Okay, so I will send a response. So it's only node 2 that will send responses to node 1 basically. So let's see what this send response does. It's a task which is here. Now in the send response task, I will just read from a sensor. Okay, so if you remember, what we are trying to do is to reply with values that we have read from a sensor. So we read from the sensor, and again this read will notify us with a read done event, which is here. So the read done event will contain the result of the read and the data that we have read from the sensor. In this case, it will be random data coming from the sensor. So we will create a new message, which this time is a response message. Okay, and well, we will put the request ID as a message ID, so we will just use the same ID of the message before, and we will put the data that we have read from the sensor into the data field of my message. Okay, so we are filling the packet with the data that we have read. Now we call again this command telling that we want this response to be acknowledged, and then we transmit the message, this time to node 1. Okay, so basically I have implemented this arrow here. What will happen is that I will again receive an acknowledgement if everything goes okay. So again the send done event will be triggered. Okay, so this is the application in TinyOS. Now let's move to the simulator. So for the simulator, you basically have to specify, first of all, a topology, okay, which is a standard TXT file, can be very, very simple. And in this case, the topology is the following. So I have a link from node 1 to node 2 with this SNR. And since links are directional, okay, they are not symmetric, you also have to specify the backward link. So from node 2 to node 1, okay, again with the same SNR. This is useful because you can actually have in reality that sometimes you have directional communication, meaning that you can reach one node from the transmitter, but the receiver cannot reply, okay? Depending on asymmetries in the radio links, basically. So you can model also this kind of stuff in the topology. So this is the most basic topology, just two nodes, node 1 and node 2, and they can communicate with each other, okay? So the topology has been declared. Now, let's have a look at the simulation script, which is a Python script in this case, which contains all the instructions to run a simulation. Now, again, you don't have to know it exactly in all the details, because mostly you will basically reuse the standard template, and maybe you will change just something in this file, okay? So you will basically reuse what is already there. So this is the TOSSIM script. We have to import some Python packages in order to start. We have to declare this variable here, which is the simulation variable, basically. And then we have to declare what kind of topology we will use, okay? And this is the file that I have just shown you. And then we have to load into the simulation a radio model file, okay? Now, what's the radio model? It's basically something like this, okay? So it's noise trace, okay? So it's something which is time variant. So it's basically a collection of values. Each value represents a discrete time. And for each value, you have basically a threshold SNR or RSSI, received signal strength. What's happening is that in the simulation, when you try to transmit a packet, so let's say that you want to transmit a packet at time 1000 milliseconds, the simulator will check what is the value contained in this file that you load, and check it and compare it with the value that you have inserted in the topology file, okay? Do you remember that -60 that I have put? And so basing on that, the simulator will decide if the packet will be received or not, or will be lost, okay? So by changing either the noise model or the number in the topology, you can create different behaviors. Okay, you can increment the number of packet loss, this kind of stuff. So we will basically use always this kind of noise model here. Then you have to initialize something here, the MAC, the radio, but this is something that you will also always do. So you can basically copy and paste here. And then you have something interesting, which are the debug channels, okay? So if you remember in this TinyOS application that I have just shown you, there were a lot of DBG statements with some prints in them, okay? And this is actually print statements which you can print or write on different debug channels, okay? And these different debug channels can be, for example, different text files, or also terminals in your system, okay? So in this case, I will use as debug output the standard output, which is basically the terminal, okay? So I will print directly into the terminal the outputs of my simulation, and then I will activate all these channels for debug. As you see, I have different channels: init, boot, radio, radio send, radio ACK. So you can differentiate channels on which to write messages, for example, depending on the priority of the debug that you want to inspect, okay? You can have, for example, a debug channel which is very, very detailed, and a debug channel which is more coarse, okay, which just lists the, let's say, macro dynamics in your application. For example, application started, message transmitted, and this kind of stuff. Or you can have another debug channel which is very, very detailed and show, for example, the content of each packet, the content of each variable, and this kind of stuff, okay? Very, very detailed information. So you have the opportunity to add different channels here. And if you look at, let's go back to the application. No, sorry. Here. And let's see what a debug statement looks like. It's something like this. So you have to specify on which debug channel you want to output your string, and then a string, okay? So you can also, like in this case, you can also print the value of some variables as you do in C, okay? Now the difference between dbg and dbg clear, it's just very, very simple, and I guess it's reported here. So dbg will output this statement, debug and the toss node ID of your node, and then the text, while dbg clear will just debug the text that you have put in the statement, okay? So you can decide what to use. You can also use dbg error with the same parameters, which will print something like error, the ID of the node which is producing the error, and then the text. Okay, so let's go back here to the simulation script. So after having activated the channels on the output, I will create the nodes, okay? Now, you see, this is very, I would say, similar to some extent to Kuja. So also there we were basically deciding a radio model, we were adding modes. The only difference is that there we were doing it graphically, which is a little bit more easy, right? Here everything is done textually, okay, which can be not that exciting, I would say, but it's more powerful, as we will see. So I will create the two nodes, okay, node 1 and node 2, and I can also decide when to make them start, okay? So as you can see here, I will start node 1 at time 0, okay, and node 2 at time 1. Now, multiplying 1 by ticks per second, meaning that I want node 2 to be boot basically after 1 second, okay? So what will happen if you understand is that node 1 will be, where's the, okay, here. Node 1 will be turned on, we'll try to send a request, but node 2 is not on, or is not on because we will wait 1 second, okay, for turning it on, okay? So the first request will basically reach node 1, and no acknowledge will come back from node 2, since node 2 is still off, okay? So by deciding when to turn on or off nodes, you can also, you know, set proper conditions in your simulation, okay? See what happens when you turn on or off a node at a particular time in your simulation, and whether your application reacts to this event properly, okay? You can simulate nodes which are breaking, for example, because they have an error, a hardware error, or they just deplete their energy, okay? So you can turn at a certain time a node off and see what happens in your network, okay? Then I will create the radio channels. Basically, these lines here are reading the topology files and creating a link for each line that you have put in the topology file. Again, just copy these lines of code. I will in the same way create the channel, radio channel, okay, by loading the noise trace inside, and again these lines just read that file. And then I can finally start my simulation. And as you can see, to run the simulation, you just have to run events, okay? So again, this final part here is something that you just copy and paste. You can decide for how long you want to run your simulation by modifying the number of ticks that you want to simulate, this kind of stuff, okay? Very good. Any question on this or curiosity? So let's just see how it works. I'll try to, so I'll open a terminal, you can do it with me. Go here, and then go to TinyOS, send. Now, if you remember, what we did last time was to compile for a particular hardware, right? And we used the TOSSIM hardware. So we wrote make TOSSIM in order to compile the application for the TOSSIM. Now, the TOSSIM simulator just supports code which is compiled for Mica Z modes, okay? It means that when you want to compile for simulating in TOSSIM, you have to compile for Mica Z, so you have to specify make Mica Z, and then you have also to specify that it's a simulation, okay? So you just add the word sim after Mica Z, okay? So you can run this. So if everything goes okay, you should see successfully built Mica Z TOSSIM library. It means that all the proper code for the simulation have been produced, okay? Now, in order to run the simulation, we just run this file, okay? The run simulation script.python. And we will basically see all the outputs from the TinyOS application, okay? So basically, that the application was booted, that a message was sent, what was the content of the message, if an acknowledgement was received or not, and this kind of stuff, okay? So let me just clear this. In order to run a simulation, you just type Python run simulation scripts.py, and then you can run it. And that's it, basically, okay? So the simulation has already finished because we are using, let me just change this a little bit. Let me just simulate for just 10 ticks, see what happens. Okay, so as you can see, these are all the prints which are coming from the Python script, okay, and here it's it's actually happening. So the simulation has started, okay, and I'm starting seeing outputs from my nodes in the simulation, okay. So far what I have done, I'm simulating just 10 events basically. So I have that the application booted on node 1, then that the radio was turned correctly on, and that node 1 was starting sending periodical requests basically, okay. So let me simulate for a little bit longer. Let me clear this. Okay, so as we can see, something is happening now, okay? What am I doing? I'm sending requests here, okay? I'm sending requests. And as you can see, I'm node 1 starting periodical request, try to send a request to node 2. If you see the source code, you can specify the time of simulation. Here is the content of the packet, okay? So all the fields inside the packet, this kind of stuff. So what's happening is that we are transmitting packets, but acknowledge was not received, okay? Why? Well, because node 2 is still in an off state, okay? Because we have to wait for basically the time, simulation time, to arrive to 1 second, okay? And then at 1 second, node 2 will be turned on. So let me simulate for a bit longer. Let me clear this. Okay, now, as you can see here, we are at 0.99 seconds. Then at 1 second, also node 2 was turned on. Okay, you see, debug node 2, application boot. Now, this means that messages that will be transmitted from node 1 will receive node 2. Okay. And in fact, node 2 now says message received. Okay, it has received a request message. Node 1 says packet sent and acknowledge received now, okay, because node 2 is on and it can reply to acknowledgement. And then node 2 will try to send a response to node 1, okay. So node 2 packet sent and ACK received at time, okay. So I actually simulated this application in TinyOS using TOSSIM. And of course, you can start by this and set up your own simulation with your own network topology, with your own application in TinyOS, your own debug statements, this kind of stuff. Okay? Any question on this? Okay, let's move on. Now, so if you remember from the first lectures, we have stressed out the fact that the Internet of Things is about items that can communicate via wireless, basically, but what they communicate is data, okay? So on one hand, we need a sensor, okay, which senses something, and at a certain point, this data have to be stored, analyzed, or managed in some way, okay? So on the other end of the channel, we have something which typically is a server, okay, a PC which stores the data. Now, how to move data from a sensor network to a PC, okay? Well, typically in real deployments, you have either a gateway which is reading from the sensor network and then transmitting to a PC, or you have a particular device which is attached to a PC which reads the data from the sensor network, okay? So then on the PC you can have everything. You can have, for example, a script that sends the data to Xively or to other cloud systems. You can have your own database, you can have everything. But at a certain point, the data coming from the sensor network should be transmitted to a PC in some way. And a nice feature for a simulator is that, well, we would like to simulate this communication between the sensor network and the PC in order to test and simulate also what will happen when we attach an application on the PC on top of the data that we get from the sensor network. Okay. Now we can do this in TOSSIM. Okay. And we will see now how to do it. And we can also do this in Kuja. Okay, so again, we can use Kuja to do something that TOSSIM can do. Okay. Now, why I am trying to show you all these tools also in Kuja? Well, because I know that using a graphical simulation environment is more, let's say, it's funnier than actually seeing debug outputs on the terminal. Okay. But at the end, when, for example, you have to, if you want to do the projects or if you want to develop something, you are basically free on which one to use. Okay. So we will see an example now, which is the TOSSIM Live example. Now, TOSSIM Live is basically an extension of TOSSIM, which can be used to communicate between TOSSIM simulation and a program on the PC through a virtual serial port. Okay, so it's basically actually like you have a sensor node which is attached to your serial port of the PC, like the USB of your PC, and you are reading data from that serial port. But in reality, you are just reading data from another program, which is a simulation. Okay, but that's useful. Now, the server-side application, so the program that reads the data, can be written in different languages. Again, I will show you an example using Java, okay? But again, there's support for C or C++. Now, we will use basically the same example that I showed you last time on the hardware, the radio count to LEDs example, where we have basically, no, sorry, we will not use that example, my mistake. Let's just see how it works. So you have also here in the TinyOS directory, the TOSSIM Live example directory. And there's a README file with the instruction of how to run it, okay? So you can follow these instructions. The application that I will simulate is what is called the test serial application, which, as you can imagine, is a TinyOS application that sends data on the serial port. Okay, it will basically send a packet each second on the serial port with a counter inside each packet, which is incremented each time. Okay, so it's an example on how to read data from a sensor network. And let's just see the application very quickly. So the only new component probably that you see here is the serial active message C component, which is exactly the same as the active message C component, so a component for sending messages, but instead of sending messages on the radio, it will send a message on the serial port. Okay, so from a mode to a PC, okay, or from a simulation to a PC. So what the application does is very easy. It will start the serial control here. If the starting was successful, it will start a timer each second. And the timer, what it does is it increments a counter and then it transmits a message on the serial port. Okay? Very easy. So we are expecting to see these messages coming in, okay, on the PC. In order to do this, we will use the TOSSIM Live application. We can see the simulation script. In this case, I have only one node, right? So I do not need to set up any topology, actually. I don't have radio links in this case. I have just one node, which is directly connected to the PC with the serial port, okay? So I do not have to specify any radio topology or any radio model. So what I will do, basically, will just create node 1, well, actually node 0, no, it's node 1, sorry, which will boot at time 0, and then I will just run the simulation. Now you see here the simulation script, it's a little bit different because I have this new let's say component, which is the throttle, which basically works like the simulation time in Kuja. You remember that you could set the simulation time to a certain percentage in order to respect real time. Well, this does basically the same stuff, okay? So it forces the simulation to run at the same time as what you want it to do. So we will see exactly messages coming at 1 message per second here. So computer time is the same as real time. Okay, what we have to do in order to use TOSSIM Live is again to compile the application in simulation mode, but since we are using the serial communication, we just have to specify here, instead of sim minus SF, where SF stands for serial forwarder, okay? So it's basically, we have to compile it respecting this. Oops, error. That's bad. Why? Okay, there's an error. I don't know why. I checked it. So this is the kind of errors that you can have in the compiler. Okay, so when something is missing, you will get some error from the compiler like this. So it will tell you, look, you have an error here, and it will tell you exactly what the error is. The problem is that this is a system error, so I probably did something wrong in the example. I have to check it again. Can you try to compile it in your system and tell me if it works or not? Funziona, vero? Okay, so I probably messed up a little bit. Anyway, okay, let's just keep, maybe I will show you next time this part. You should, if you follow the instruction there on the README file, you should see messages coming into the Java application. Now let's just move to another part, which is actually really the same. So instead of showing how to communicate from the simulation to TOSSIM Live, I will use Kuja, okay, so the graphical simulator for Contiki. I will load the executable for this application, and then I will connect the Node-RED interface, if you remember, the web-based interface, in order to get data from the simulation, okay? So let's see if I can show you this. Yeah, sorry, I was doing something completely wrong. It's not the Sendak application that I want to compile for simulation, it's the TOSSIM Live application. So yeah, sorry for this. So let's see if it works. C minus SF. Yeah, it works. So I was compiling a different application. That's why it was not working. So now, erase the last, let's say, 7 minutes of what I have said. So basically, now I have the application which is compiled for simulation with the serial interface, okay? What I have to do is just to basically follow this, where is it? Here, the README file. So you can also follow this README file here. So we have compiled the application with support for serial forwarding. Now, in order to use this TOSSIM Live, we basically have to open what is called the serial forwarder, which is an external program, a TinyOS program, which forwards messages from the simulation to somewhere else. And this somewhere else is the actually program that we will use to intercept these messages. Okay? So I will copy this, open the serial forwarder, like this. And this serial forwarder is basically a very little panel which just tells you how many packets have been forwarded from the simulation to the program that you want to use. And then there's this Java program here which is called test serial, which can be opened. Okay, and let me just open it first, and let's see what it does. So it basically listens for messages. The source code is here, testserial.java. It basically listens for messages, okay, and it will just print on the output that I have received a packet, okay, with a sequence number inside. The important thing is that this is code that you execute on the PC, okay, not on the simulator, okay. So here you can attach your application if you want. You can attach, for example, data processing, data storing, data plotting, whatever you want. Here now you are on the PC side, on the server side, okay? But of course, in order to run it, I have to run the simulation, right? Because so far I have just opened the serial forwarder and a program that listens to messages, but the simulation is off. So I have to run the simulation script in order to get this node sending something on the serial interface. So I will just run the simulation. Okay. And you can see the node 1 is sending packets here, and this one is receiving packets. Okay. So this is the simulation, this is the sensor network that you are simulating. It's transmitting packets. And this is the server side, which is receiving packets. Now, from here on, you are on the PC, on the server side. You can do whatever you want and on the PC, okay? So, again, an example of how to communicate. Any question? Now we will see the exact same thing, but using Kuja, so the graphical simulator, and instead of having a Java program like this, which receives data, we will use the Node-RED system to receive data in the web application, okay? So that should be a little bit more interesting. Now, the application that I'm simulating is just transmitting one message each second with an incremental counter. As you see, it's just incrementing a counter. So let's stop everything. Now, if I want to use the Kuja simulator, if you remember, I have to compile for the TOSSIM node instead of the MicroZ node. And in this case, I don't even have to specify that it's a simulation because it's a complete different environment, okay? So let's just clean it before. And then let's compile it for TOSSIM, okay? Okay. Now I can close this. I have to open the Kuja simulator. It's a little bit slow when I record from QuickTime. Okay, so let's create a new simulation. Just create one. I will add a mode. If you remember, if I want to simulate TOSSIM, I have to create a sky mode. I have to browse here, TOSSIM Live, build, TOSSIM, and the executable file for the simulation. Okay, I will create just one node, and I have my node here, which is doing nothing because the simulation is not started. Let me just put 100%, so meaning that I want simulation time being equal to real time. And let me just open the Node-RED environment, okay? I don't know if you have this. I will probably create a couple of slides on how to install it. So I have shown you the first. Oh, sorry. First I have to run it into the terminal. I will provide some slides on how to set up Node-RED on the system and how to get everything working. Or if you prefer, I will put another version of the virtual machine online with Node-RED already installed, so you can erase your virtual machine, download the virtual machine, the new virtual machine. That's very easy. Okay, should be ready. It's really slow. Okay. Now I have prepared this very little example, which basically reads messages from Kuja. Then there's a function that I have written to parse the message, so to read the fields, and then I have the basically to debug nodes to print here the messages that will arrive. In order to run this, you have to enable the serial port on the node here, and you can do this by clicking on serial socket server. It will basically open a connection between Kuja and Node-RED. Okay, see, client connected. I will start my application. Okay, so the application has started. This is starting transmitting packets, and in Node-RED here, you see, I see numbers, which is basically the payload of the message which was transmitting from the simulation in Node-RED. Okay, so what I'm doing here, basically I'm connecting a server-side application with a simulation of a sensor network. Now you can imagine this is very powerful because on one side, on Kuja, I have my TinyOS application running. I can have several nodes doing sensor reading, or you can have a particular protocol which is working on. But at the end of the day, some data will come out of this sensor network to go somewhere. And this somewhere, in this case, is Node-RED. Okay, so it's a web page where you have the data here, and now here you can append to this simple chain some other processing. For example, you can do some database writing, reading, correlating data, plotting data, and all this kind of stuff. And in fact, one of the projects will be about this, so about exploring Node-RED capabilities, okay? Since it's new to me as well, you can, implement something very, very easy in the sensor network, attach Node-RED, and explore what you can do with Node-RED, okay? So basically, create an IoT application in the web, okay? So yeah, what I will do is probably just put another version of the virtual machine on the website, erasing the previous one with Node-RED installed, so you don't have to waste time and you can use it directly. And you can use the new examples as well. And maybe provide 2 or 3 slides on how to use Node-RED just to begin. I mean, I started it couple of days before these lectures, and it was quite easy to set it up. Okay, so that's all for this lecture. If you have any question or any issue with all the tools that we have seen, I can stay here 10 minutes more and we can discuss it a little bit.